Lesson 10-1. Use properties of tangents. By the end of today's lesson, we will be able to successfully use properties of a tangent to a circle. Now, I would like you to pause the video and write down all the definitions to all these vocabulary terms, and then continue and play the video to finish your notes. The circle. The circle is a set of points in a plane that are equidistant from a given point. So, what this definition means is you have a point that's called the center, which is your second vocabulary term, and that is equidistant to a set of points that forms a circle. And again, the center is the point from which all points of a circle, so all points of the circle, are equidistant. And the radius, this distance from the center to a point on the circle, to any point on the circle, is called the radius. And a chord is a segment whose endpoints are on a circle. So if I draw a point here, another point here, and I connect these 2 points, we can call this a chord. And the diameter is a chord that contains the center of the circle. So I'm going to label C for center. So if I extend the radius for the other side, this part would be called a diameter. And the secant is a line that intersects a circle in 2 points. So this will be called a secant. And the tangent is a line that intersects a circle in exactly 1 point. So I can do this. This would be the tangent. And if we were to draw a radius from the center to the point of tangency, this is actually perpendicular, and we will actually talk more about that later. Example 1. Tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of a circle C. Now if we look at segment BC, this is obviously the radius. And line EA intersects 2 points on the circle, so we call this a secant. And then ray DE intersects a circle in exactly 1 point, so we call this a tangent. Example 2. Use a diagram to find the given lengths. Part A. The radius of circle A is 2 units. So I just look at center A and count 2 units. And the diameter of circle A would just be double 2 units, so that would be 4 units. And the radius of circle B, so this would be 1, 2, 3, 4 units. And the diameter of circle B would be 8 units. Okay, so that was just a quick review. And example 3, tell how many common tangents the circles have and draw them. So common tangents would just mean that a tangent line that would touch or intersect both circles at a point each. So if I look at these 2 circles here, we can draw one from here, and they have tangent to the big circle in 1 point and tangent here as well. And we could do this. We can also do this. So there's 3 tangents. And part B, because these 2 circles intersect in 2 points, we can't draw a tangent line in between, but we can still draw a tangent line that intersects each circle in 1 point from each side. So that makes 2. And then for this one, we could do this, and we can also draw this, and that's 1, 2, 3, 4 tangent lines. And for this concentric circles, we only have 1. Theorem 10.1. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So I mentioned a little earlier that if you have a line that's tangent to the circle, then it makes a perpendicular angle with the radius. And to prove this, we need to use an indirect proof. So assume that OP is not perpendicular to line M. Then there must be a point X so that OX is perpendicular to M. So we're assuming that this angle is 90 degrees. Then OPX must be an acute if we make the previous assumption. Therefore, by theorem 5.10, segment OP has to be greater than segment OX because this 90 degrees is greater than this assumed acute angle. So we know that the radius OE is equal to OP. And if we substitute OE in for OP, we get OE greater than OX. But how can OE be greater than OX? So that's impossible. Therefore, we can state that OP is perpendicular to line M. Example 4. In each diagram, segment RS is a radius of circle R. Is segment ST tangent to circle R? So to find out, we need to check to see if these form right triangles. So I need to first let you know that 26 here refers to the entire length of TR. And I'm going to simplify the sides by 2. And I find out that these sides form a Pythagorean triple. If you add these together, it's 169, so yes. And for this problem, I would like to indicate that the length 8 here refers to this point, to point T. And I don't want you to worry about this right now. On the test, I'll make it very clear. And this part will be 5, so the length of RT will be 13. So this also forms a Pythagorean triple, 5, 12, 13. So yes. And this one, 7 refers to the length from this point to T. And we have 12 here, the RT is 19. And if we check, 16 squared plus 12 squared equals 19 squared. This doesn't equal 19 squared, so no. This is not a right angle. So ST is not tangent to. Example 5, part A. In the diagram, B is the point of tangent C. Find the radius R of circle C. So I know this is gonna be the right angle here, ABC. So I need to use a Pythagorean theorem. 77 squared plus R squared. And then we want to know if that equals 49 plus R squared. So here we have 5929 and 2401 plus 98R plus R squared. Cancel this out. Then we have 98R equaling to 3528, and R should be 36. Part B, in the diagram, K is the point of tangent C. Find the radius R of circle L. So we have to do the same thing here. So 32 plus R squared equals R squared plus 56 squared. So 32 squared give you 1024, and then we have 64R squared, R, and then plus R squared, and R squared plus 56 squared is 3136. Cancel out the R squared, and then for the next step, I can write 64R equals 2112, and then R should be 33. Theorem 10.2 states that tangent segments from a common external point are congruent. So if S is your external point, meaning a point outside of the circle, and if they meet at two different tangent points on the circle, then these two segments here have to be congruent. How do we prove this? Is by forming these two right triangles and use the HL congruence theorem to prove that these two triangles are congruent, and by CP/CTC, RS and TS are congruent. Example 6. Segment QR is tangent to circle C at R, and QS is tangent to circle C at S. Find the value of X. So with this piece of information, and by using theorem 10.2, I could just set 32 equal to 3x plus 5, and then x would equal to 9. Let's do one more practice. Segment RS is tangent to circle C at S, and RT is tangent to circle C at T. So again, external point at R, find the value of x. So we could just do x squared equals 49. We'll just take the square root. Positive, negative. So x equals to positive negative 7. Now you must be wondering about the negative 7. If you plug it back into x, it's still positive. So you could have two answers.